Hello everybody, my name is Nathan and welcome to today's study club video. And today we'll be discussing about maths and trigonometry, and specifically we'll be talking about sine, cosine, and their derivatives. So what are sines and cosines? They are pretty unique functions because they're probably one of the very few functions that are repetitive in nature, and they repeat between a value of -1 and 1. Specifically, this is for cos x and sine x. And both of these functions are also separated by a phase difference of pi over 2. What do I mean by this? Well, I graph both of the functions in GeoGebra, and as you can see, cosine has a peak value of 1 at x equals 0, whereas sine has that same peak at x equals pi over 2. This means that cos experiences that peak much earlier, pi over 2 earlier, in fact, compared to sine, and this is what is meant by the phase difference. And from class, we know that the derivative of sine x is cos x, and the derivative of cos x is negative sine x. But can we visualize this geometrically? So I found this method by Mr. Grant Sanderson, better known as 3 Blue 1 Brown on YouTube. And yes, there is a way. And it was very intuitive and helped me to visualize why the derivatives of trigonometric functions are basically each other. And I hope that you guys will be able to visualize it as well. And I'll try my best to explain it in my own words and to my own understanding. Let's begin. So I started by choosing a function. I chose the cosine function and I graphed it here. This is basically the graph of cosine x. And of course, we need to plot points in order to use it for our analysis. I plotted 5 points here, A, B, C, D, and E. And although you can't see the values yet, don't worry, they're on the next slide. So I chose these values specifically because they are special angles. They have these unique values, and special angles are basically 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and so on. But I decided to represent these in radians because it's more convenient to do so. The point is, the point of this video is not to learn how to convert between radians and degrees, but just know that pi over 6 corresponds to 30 degrees, and pi over 4 to 45 degrees, and so on. And so we have the values of these cosine values, and all you need to do is just insert them into your GDC, and you make sure the GDC is in radians mode though, and you'll get the same values. Let us do the same. Let us input these same values, the same angle specifically, into the negative sine value, because negative sine is the derivative of cos. Now that we have done that, notice that cos and sine are basically opposites of each other. At negative sine 0 equals 0, cos 0 equals 1, negative sine pi over 2 equals negative 1, and cos 0 equals 0. They're basically opposite patterns of each other. But the key here is to think of the cosine value as the actual function that we're drawing, and the negative sign as the gradient basically of how much the function changes, whether the function is increasing or decreasing. And we'll show this in the next few slides. Now at x equals 0, remember cosine 0 equals 1, which corresponds to the value of 1 at 0 here. And the negative, when we insert it into negative sine x, when we insert 0 there, it equals 0, which makes sense because the gradient is flat, as we can see. It corresponds to 0, right? Which is why there's no rate of change. It's staying still at the top there. We do the same thing to pi over 6. The value of cos pi over 6 is square root of 3 over 2. And the value of negative sine pi over 6 is basically negative half. This is larger than 0, which means that the gradient is no longer stationary. It's negative now, as you can see here. And as we move on to pi over 4, the value of negative sine pi over 4 is negative square root of 2 over 2, which is larger than negative 1 over 2, my bad. And as you can see, the gradient is more negative and thus sharper. See it all the way to pi over 2, and we find that, negative sine pi over 2 is negative 1, right? It is, the gradient there is sharpest and most negative than the previous values that we've inputted. So what can we find from this? Notice that at cos 0, the gradient of the function is 0 because it corresponds to negative sine 0, does it not? It means that there is no rate of change there. Let's draw more points to see if this like correlation still holds. I plotted more points there, F, G, H, and just notice that these angles are basically the same special angles before, but above 90 degrees, we can put that into our GBC again. We get these values. We do the same thing where we insert the values both for cos and negative sine, and we get these values. Take note of these values again, and let's proceed. Now notice that at 2 pi over 3, when we insert that into negative sine, we notice that the value is negative square root of 3 over 2. As we've seen from the table before, after pi over 2, the values of the gradient slowly decreases to 0. And we can see that because negative square root of 3 over 2 is less than negative 1. It is less sharp than negative 1. Insert 3 pi over 4 now into negative sine x. And we obtain negative square root of 2 over 2, which again is less sharp, and the value is smaller than negative square root of 3 over 2, as we can see here. We do the same thing again when we want to insert 5 pi over 6 into negative sine. It gives us negative half, which again is less sharp than negative square root of 2 over 2. And finally, when pi into negative sine x, we obtain 0. Another flat gradient, right? Which corresponds to the to the value we found in the table that we calculated in the tables before. So from all of this, what can we conclude? You can repeat this for an infinite period. You can repeat this forever if you want, but you'll obtain like this alternating between negative and positive gradients wherever you go. And in the end, what you can conclude is that the rate of change of cosine or its gradient will always depend on negative sine. On negative sine x, essentially. And our investigation before has just proved that that is the case. Remember, the important thing here is to think of cosine as the actual function and negative sine as basically how the function changes over time. Now we've basically found we've basically explored the visual interpretation of why this is the case. And these are some of the references that I've used, and hopefully this video has helped you guys. Thank you so much, everybody. Thanks for attending this study club video.